Hello and welcome to part 2 of our ABG presentation. So we were discussing about bicarb, carbon dioxide, Hasselbalch-Henderson equation in part 1. Now how bicarb helps in maintaining or buffering it? It goes and combines with a hydrogen ion, and so this equation forms water and carbon dioxide. Okay, so we need to remember that it is a major buffer in taking out any extra carbon dioxide from the body. Okay, so let's see how bicarb can be lost from the body. Okay, now there are two mechanisms by which bicarb can be lost from the body. One is by combining with the hydrogen ions, or the other is by simply losing it, which means the patient is having diarrhea, losing bicarb, and having an acidosis. So let's first focus on this. How does it combine with hydrogen ion? So if we have added a weak acid to the body, this can be lactate, citrate, or any weak acid. So once this weak acid is added to the body, this releases a conjugated base and hydrogen ions. Now these hydrogen ions are buffered by bicarb and then changed into water and carbon dioxide. Okay, so what does it mean? It means now this extra negatively charged body will be available in the blood, and it will add to what we call as an ion gap. Okay, so let us see what is an ion gap and how do we calculate it. So it's a simple rule that number of positive charge and the negative charged ions in the body will always be constant. So our major positive charges which we consider in our body are sodium, potassium, and then the negative charge are bicarb and chlorides. Now ideally speaking, the sum of this minus the sum of this should be 0. In fact, potassium is in such a small concentration that we don't even consider it in calculating an ion gap. But actually, when we do this, I'm sorry. We get a number which is 12. So what does it mean? Well, that means, see, ideally this should be 0. So that means there are certain things which we are actually not able to see in this equation and which are present in the blood, and they are negatively charged. See, there are a lot of positively charged ions like magnesium, calcium, which we don't consider in this, and there are negatively charged stuff which we don't consider here, like phosphorus, sulfate. But we are getting a number 12, which is a normal number here. So what is it which is actually governing this? Well, the answer is albumin. So we don't consider albumin here, but albumin is actually contributing to the normal anion gap in body. Now one thing very important which I need to mention here is our normal serum albumin average is 4. So if somebody has an albumin of 4, his normal anion gap or expected anion gap would be 12. Now what happens if this goes down to 2? Well, the expected anion gap should be 6. So this we need to remember every time when we are reading an ABG. we should be inquiring about the normal or the present albumin, serum albumin of this patient. And the expected anion gap would always be 3 times the present serum albumin level, which is evident from this. Okay, so that's the anion gap. And now going back to what bicarb does to the hydrogen ion. So there was hydrogen, and we saw that bicarb came and buffered it, and we had extra line negatively charged body in the blood. Now this contributes to an anion gap, further increasing it. So, which means that if there is 1 unit of hydrogen ion released, it will consume 1 unit of bicarb, and it will release a negatively charged ion which will contribute to an ion gap. So for example, if somebody's anion gap, considering his albumin is 4, is 20, what does it mean? Okay, let's see. So normal anion gap would be 12. Now he is having an anion gap of 20. So that means there is a gap which is also known as delta gap of 8. Now what does it mean? It means that there are 8 negatively charged ions circulating in the body, which is contributing to increased anion gap. So if there are 8 negatively charged ions in body, that means they must have released 8 protons in the body, right? So if they have released 8 protons in the body, that means they would have been buffered by 8 bicarbs from the body, right? So if you take normal bicarb as 24, the present bicarb on your ABG strip in this patient particularly should be 24 minus 8, which is 16. Okay, so if somebody is having an anion gap of 20, that means it is 8 more than 12, which was 12 was normal. So that means there are 8 units which have released 8 units of protons in the body, which were buffered by 8 bicarb. So that means your body should be down by 8 units of bicarb, and now your bicarb on the ABG strip should be 16. Okay, as long as it is only 16, this becomes a case of anion gap metabolic acidosis. See, bicarb is going low, so it is acidosis. It is metabolic because it is involving bicarb, and it is anion gap because the anion gap has increased. Now, if you find this not as 16 but as 20, what would that mean? See, 8 protons are released, so 8 bicarbs should have been consumed. Now the reading should be 16, but it is 20. So that means there is a gain in bicarb. The bicarb is being added to the blood from somewhere. So that means this patient would have metabolic alkalosis as well. Okay, well, that's pretty much about the part 2. Join me for part 3 of this ABG discussion. Thank you very much.